Hi, I'm Ben-Yaakov. This presentation is entitled Oscilloscope Measurements in Power Electronics. This is part number 1, Single-Ended Probe. So this is the first part of a two-part sequence. The second one will deal with a differential probe. Typically, we'd like to measure in power electronics signals of this nature. We have here a half bridge, two drivers, two transistors, and we would like to have a look at, say, the voltage between the gate of the lower side, VG1, and the voltage across the drain to source voltage. And then, of course, we'd like to see also the gate of the upper transistor of the high side, which is sort of riding here and connected to the high voltage side. Now the system will have a local ground, but not necessarily connected to earth, that is to the grounding of the building or the structure. This is really a local ground. We call it a ground plane, which all the components will be connected to it. So the way to look at the signal is, of course, to use an oscilloscope. And typically an oscilloscope will have 2, 4, 8 number of channels. And here I'm showing one channel with one single-ended probe. This is the tip of the probe, and this is the ground side, which is connected inside actually to ground. Now, in many applications, we are using a 10-to-1 probe. It's an attenuating probe. It is increasing, on one hand, the impedance of the probe, because normally for not very high frequencies, the input impedance will be 1 megohm in parallel to 5 picofarad. This will be typical of a oscilloscope for very, very high, the gigahertz region. We are using, of course, 50 ohm, which is not relevant to our discussion here, because the impedance is also very low. We cannot use it in power electronics. So we have a oscilloscope with 1 megohm, and normally the probe is adding, say, 9 mega ohms, so therefore it attenuates by 10. However, if we'll just add a resistor of 1 or 9 mega ohm, we're going to have a low pass filter here, and therefore the signal, even if we'll feed a square wave here, will look at the scope something like that. So therefore, there is always in a probe a capacitor across this resistor. In fact, it is an adjustable capacitor, because you cannot know, or you don't know exactly the value here. So this is an adjustable capacitor. And the point is that if you have a network of this nature, resistor, capacitor, this is the input of the oscilloscope, this is the probe, then if R1, the time constants, are equal here, R1, C1, R2, C2, then the transfer function between here and here is going to be flat. So by having C2 adjustable, there's normally a place to sort of for a screwdriver, you adjust it, you can adjust it until you get a nice square wave on the scope. When you are feeding it with a square wave, normally an oscilloscope would have a test point, an output of a square wave, normally 1 kilohertz, and then you can just connect the probe to this source and then adjust it until you get a nice waveform. Too much, too little will be something like this, too much will look like this. So you have to be just in between to get this nice waveform. So this is at the very beginning. You test the probe, see that it is functioning properly, and now we go to the actual problem, and we are now starting with the low side. So we want to measure, say, the two signals here, gate to source, drain to source, with reference to the ground, or the local ground. So here it is. We have the scope, we have the converter. This is usually a coaxial cable. Then the outside is connected to ground, and here's the tip of the probe. We say we like to measure the ground to source voltage or waveform, more precise. Unfortunately, we do have a problem that if you have two instruments or two units, then between the grounds there's going to be a potential difference that I'll call it ground noise or ground potential if you wish. So there is a difference, so this point and this point are not at the same potential. And this brings up some problems, and in particular it can corrupt the waveform that you see here in adding some spikes to it which are irrelevant to the voltage that you actually want to measure. So let me try to explain what is the nature of this source or this voltage, and how can we test for it to make sure that our measurement, what we see here, is indeed correct. That is the problem that I have, is that I'm measuring something, I'm seeing some spikes, and the question is, are these spikes correct? Or maybe they are due to this ground potential difference. So you can have a look at this difference by just, with the probe, looking between the ground, between here and here. This will be, say, the ground side, this will be the tip of the probe, and you'll see noise. There's no question about that. If this is a converter running at some frequency, you'll see spikes, etc. But this really doesn't tell us as to whether this measurement will be okay or not. Okay? So before, however, going into the question how to test whether your measurement is correct, let me just explain what is the reason for this ground noise or ground potential difference. Now, it's important to realize that there is always a ground potential difference, and this is due to the fact that through the ground, either wires, traces, or even ground plane, there is current passing, and the path has some impedance, so therefore the product of current time impedance brings about a potential difference. So the notion of having a, say, ground plane in which the potential is equal all over is just incorrect. Of course, there is a degree. The question is, what's the impedance? The question is, what is the current? In high power converters, these difference could be tens of volts. So one has to be aware that when you connect to ground at one point and then to ground to another point, these 2 points may have a small or large potential difference. So what is the reason for that? There are two cases that I'm here explaining. One is when you have both the scope and the converter connected to ground. Okay? Now, it means that there is a point which is actually connected to Earth. There's a conductor that is pushed into ground, and then it comes up the building, and eventually the scope is connected to it, and then the converter is also grounded and it's connected to it. Okay, so this is one case. This could be a converter, could be any other instrument, could be a function generator or anything like that. Now, through these lines, there are currents going to ground. Okay, there are currents going to ground, and since there is a impedance to these lines, here it is. The first approximation will be a resistor and inductance in both cases. Therefore, there is a voltage drop here. There is a voltage drop here. Obviously, they are not equal. So therefore, there is a potential difference. Okay? So let's ask ourselves, why is there a current? Why is there a current going here? And it'll be the same thing for the scope, but I'm concerned with the converter. Let's talk about the converter. Okay? So here we have a converter, and I'm showing here that it is connected to ground here, okay? This is the ground side, earth, and this is the ground plane of the converter. Now we have here a isolation transformer. That is, the converter is fed from the line. This is the mains here, 220, 120. And then we have some rectification. I'm showing it in a sort of a generic way, just a diode. There's some rectification. And then we have this high voltage line, and here is this half bridge we are talking about. Okay. Now the transistors are connected to a heatsink through some usually insulator because if this is a transistor, it's a TO220, so this is actually the drain, and this is the heatsink, so you have to worry about the voltage difference, of course, and you need isolation between them. Now, due to this, there is a capacitance between here and the ground of the system, because the heatsink will be grounded. Even if the transistor is just in the air, not connected to anything here, still there will be stray capacitance between its body and the structure here, and the ground plane or the box or all other metal units which are connected to ground. So there is always some capacitance. The question is, what's the size of it? Now, here we have now this half bridge, which is switching up and down. And at this point, we're going to see here like a square wave. And you might say that you have here like two voltage sources which are changing and causing this point to go up and down. And normally the transitions are very fast. That is, it's going up fast and going down depending on the switching frequency, transistors, etc. But we are talking about microseconds and lower, that is nanoseconds, even in the case of, say, very high transistors. Now, these transitions are passing, or the voltage here is causing a current to pass through this capacitor. And therefore, we have now a path starting here, going this way to the high voltage, going here, going to ground, going here, and coming back. Always look for the loop. That is, in order to understand what is going on, you have to see the complete loop, how it starts and how it comes back to the same point. So here we have this source here. This source is feeding here, and I'm showing here that other path here. There are other possibilities. I'm just showing one way in which we see clearly that there is a path of current. So there is a current flowing here through this ground, or through this point, which is the ground of the system, to the actual ground. I'm showing it as neutral of the line, and then it comes back through this capacitor. So whatever you do, there is always some current going to ground. So going back to this unit, then you see that there is a voltage drop here, there is a voltage drop here due to the impedances, and there is always a difference. So going back to our problem, we want to see whether our test bed here is sensitive to this difference, okay? A way to do it is to short the tip of the probe with ground. Touch the ground of the converter, this point. This point now is at high potential over this. These are shorted. You would think that the voltage that you'll see here, or the trace, will be zero. Well, normally it is not. The question is, how large is it? This test is giving you actually the baseline. That is, afterward, if you move the tip of the probe to the gate and see a signal and see some wiggle on it, some spike, compare it to the spike or the signal that you see when these two are shorted. And if it is about the same, this means that the measurement of the gate, of the spike that you see, is not real. It is due to this common mode rather than the signal itself. So this is extremely important to do just before you do the measurement. Just short the two, look at the signal, and you can record it or just keep it in your mind. And then when you do the measurement, look at the signal that you see in here as a reference. Anything above it is real. If it is about the same, then it is not real, it is due to the common mode. So another question is, if I touch the tip of the probe to the ground and then to this point, why won't I see 0 here? I mean, what's the reason for it? So let's have a look what is really happening. Here is the amplifier of the scope. This is the scope here, the oscilloscope. This is the probe here. And here we are touching this ground, which is different from this ground, and there's a potential difference between them. And these two lines are connected. This is a single-ended input. This is usually what we have in an oscilloscope. There are oscilloscopes which are differential. I'm not dealing with it in this video. I'll discuss it in the next video or forthcoming video. The possibility of using a differential, either amplifier or probe. But a regular oscilloscope would have a single-ended input, meaning that there is one line and then there is ground. Now usually this ground is not connected directly to Earth or to the connection of ground, but rather through some impedance. So now we have a difference here between these two, and I'm shorting this and this. And what happens is that I've actually put a wire across this voltage source, and there's going to be current through this ground part, through the sheet. The magnitude of it could be fairly high, by the way. And since this is a low impedance voltage, that is, the source is coming out of a low impedance equivalent source, and it is low impedance because it is generated by the voltage drop on a ground line, and ground line have very, very low impedances. So the end result is that this source has a very low internal resistance, you might say, and therefore putting here another line, another cable will not short it. Current will pass, but still the difference will be maintained. So now we do have on this line a voltage difference because there is a current here, and this line has some resistance or impedance, and therefore there is a difference. And consequently now the voltage that you measure by the amplifier is actually this difference that is starting from here, 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 here. The amplifier sees the voltage here, and this is what you see on the oscilloscope. So this means that oscilloscopes are sensitive to common mode voltages. It really depends on the quality of oscilloscope. There are means to make it smaller. So it can be reduced, but eventually every oscilloscope is to some degree sensitive to a common mode voltage with a single-ended probe. So this is something you have to do, something you have to measure just to get the baseline before taking the actual measurement. So this is the first problem that we have the ground potential difference. Another problem that you might have is that the converter has magnetic elements, wires that carry high current, and therefore there's a lot of magnetic flux around, and some of this magnetic flux can enter this loop here. This is the ground side, this is the tip of the probe, and once this flux is entering this loop, then of course you'd see a voltage here, which is N d-phi-d-t. In this case, N is 1, because you have one loop here, or one turn, and therefore you might have quite a bit of a noise coming out of this. So the objective would be also to reduce the area of this loop as much as you can do. One way to do it is sort of to wrap the ground. If you have a long lead for the ground, wrap it around the probe and then connect it. This will reduce the area, but this is, if the flux is strong, this will not be sufficient, especially at high frequency, and if the d-phi-d-t is very high, that is high rate of changes, you'll still pick up quite a bit of noise. So the next thing to do is to take off the cover of the probe, and then you have a piece of metal here, which is actually ground, and then to wrap a wire around it. This will be a bare wire, conductor, and then you have an end of it, so you generate or make a two-tip probe, and of course you'd like this area to be as small as possible. So this will reduce the area quite a bit. And when you design the PCB, and then you better prepare a test point for this, and then a ground point for this. So when you do the measurement, you just take this probe, this modified probe, and insert them here, and then you can get a minimum area for the interference. Now, what about the high side? Obviously, if you take the scope, which is grounded, and then you connect it to the high side, there'll be a short, because this is a high voltage, and through this ground wire, there'll be a short, so you cannot do that. There is a sort of a solution, which I do not recommend, and I think it's a bad way to go, and that is to make this scope floating. In this case, what we do, or we can do, is to take an isolation transformer. This is a mains transformer, 50 or 60 hertz, and then have the scope actually floating here. That is not connected actually to the mains, and also not connected to ground at all. That is, there's no ground wire here that is connected to the ground. So the scope is sort of floating, and then therefore if you connect this ground side, which is now not connected to ground, to the point here, which is sort of switching up and down, could be high voltage here, then there's no danger of a short circuit. But there are many other problems, and let me point at least to two of them. One is safety. Now what happens is this line here is now at high voltage. It is not designed for high voltage, and you can get electrified. Now, usually it has some isolation on it, but it's not designed for this type of an operation. Also, if you'll have bare parts, or sort of the casing of the scope might be connected also through some impedance to this line. So if you touch the body or the casing, you might also get electrified. So there is a real safety issue here, and I think it is dangerous not to ground a test instrument. I think any test instrument should be grounded, unless it's a portable like a voltmeter. But any other one that is connected to the line should be grounded. But there's also an issue of EMI here. Although it is sort of isolated, there is some interwinding between the winding. There is a capacitances because this is a low frequency transformer, and therefore the capacitance between primary and secondary could be fairly high. So for the high frequency component, it is like, you know, a low impedance, and therefore there is a path here that starts here, goes through the ground here, through here, and then comes back into the ground plane or ground side of the converter. So again, you might have a severe EMI problem even if this is floating. So this is really not solving problem of EMI, and again there is a danger of electrification. So the correct way to test the high side is to use a differential probe. I'm going to discuss this in detail in a forthcoming video. And in this case, with a differential probe, it is safe. Not that it doesn't have its own problems, but this is the way, or the correct way, to measure a high side signal. So before actual test with an oscilloscope, what one has to do, first of all, adjust the probe for flat bandwidth, then test the common mode EMI to see the effect of the ground potential difference and to see how much does it affect your reading. This is the baseline. And of course, you have to make effort to minimize the loop between the tip of the probe and the ground side. So this brings me to the end of this presentation. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.